All right. Hopefully the others will rejoin. All right. So Chapter 7, IP addressing, is where we're up to this week, and this is where all those worksheets that I've put up over the last few weeks come in their own. So none of this chapter should be new. It's basically where we do the conversion between binary and decimal. There's a few concepts we introduce: network portion, host portion. We talk about the extended notations that are used in IPv6, and we come to testing, so using our ping and trace routes, which we've done a bit before. So binary is 32. Our IP address is made up of 32 binary digits, which are divided into 4 8-bit octets, and we then convert those binary values using a positional value of the binary bits to give us a decimal value, and we call that representation dotted decimal notation. Now, as per the lovely notation values, we've gone through this on the whiteboard in that last term. Each bit value, be alright if I can move forward on that. So each position has a represented value. So if that bit is turned on, it's worth that value. We add those values together, and that's what our new dotted format value for the decimal notation is going to equal. I'm glad it's sounding better than the first attempt. Okay, so IPv4 addressing is divided, like any addressing, between the portion that represents the network and the portion that represents hosts. Now, going back to our first example here, we have a /24 network, which means the first 24 bits represent the network, and the last 8 bits will represent the host. So this is what we're representing here. So these 24 bits are network portion. Those remaining bits to the right are host portion. This is always the order. So the bits on the left hand side of the address space always represent the network portion. Those on the right represent host. So as we've gone through setting up host machines before, you know we have to have an individual IP address and a subnet mask entered and a default gateway. Now, if we have all ones representing the network portion, that equals 255. So 24 ones is 255, 255, 255, and then the 8s are all zeros because they're turned off. So converted that into binary, we end up with this notation down the bottom. And the basic logical ANDing, I won't go through all that. In very basic terms, the host portion turns any value of that's above to a 0. So with the ANDing function, the host portion is turned to zeros, and that leaves you only with the network portion of the address left. And this is the portion of the address space that the routers use to make their routing decision on. Because talking in terms of the old network infrastructure, a network address represents the cable that the devices are all connected via to the router. Remember that Ethernet was designed for straight coaxial cable with T pieces on it. I should comment on that one. So basically, this is just subnet masks and prefix links. Nothing unusual here in that we have all ones representing the network portion. You just count them up, and using CIDR notation, which is this / and then a number, tells you how many of those ones there are in the subnet mask. And using the same positional bit values as we've looked at earlier, you can convert them into dotted decimal notation form just as easily. Network host and broadcast addresses. So there are basically 3 types of addresses in every network. We've got the network address, where all the host portion is zeros. The broadcast address, where all the host portion is ones. Anything in between those 2 values is known as host addresses. So first host, first bit value 1. Last host is where all the bits are on 1 except for the last. Okay, so 1 shy of the broadcast address. So converting that out again, so .1 to .254 and .255 is the broadcast address. Now we'll explain. Basically, the broadcast address is where we send a message to every machine on that network portion. So using Windows Calculator to calculate network addresses, can do it that way. Feel free to do it. But if any of you are looking at taking any of the industry certifications later on, you need to be able to do all of this by hand, because you do not have access to the Windows Calculator in the Prometric exams, just as a heads up. And so the lab there, converting IP addresses to binary, basically just like the worksheets I've handed out previously. And alright, so most computers will use dynamic host configuration protocol to obtain their IP addresses off a server. Now, in a home environment, that is generally speaking your router, and it just pushes out the address and says how long that address can be used for before having to renew the lease and confirm the addresses again. Okay, transmission types are normally unicast in the IP world. So this is where it's a 1-to-1 transmission. We do also have broadcast, where we send 1 to all. So every other device on that network picks up the transmission. Multicast transmissions are a little bit different in that they're like subscribers. You need to subscribe to the service to actually get the transmission. The other machines will not listen for the message sent on a multicast address. Multicast addresses are from the range 224 to 239 in the IPv4 address space. And if you convert that out to actual so if you look at the value of 3 digits in the first, 128 plus 64 plus 32, okay, and the next value has to be a 0, because if you add 16 to that is 240. So anything starting with that address space is a multicast address. That's how it filters these addresses. Just looks for that starting combination of in that first octet, and it identifies it as a multicast address. So we have a packet tracer activity to do. Well, can only do packet tracer activities, and with this, especially with the remote. I'm hoping everybody has downloaded Packet Tracer for their home PC and are doing the labs in Packet Tracer. I know some of you aren't even logging in. That will become problematic for those individuals later on. Private addresses are the address space that is used within your network and is not seen by the internet. Service providers will not route these blocks of addresses because they get reused by everybody. Okay, so the most common address that home devices use is our 192.168.1.1/24. All right, so our 1.0 network. All right, so that's the most commonly used network address in the domestic market. And all these networks, the 10 network, which is what used to be known as Class A, the 172.16 to the 172.31 was known as Class B network, and the 192.168 address range was known as a Class C network private address. Classes were disbanded because they were inefficient. Every block of network addresses had to be the same size. You couldn't have variations. So a lot of addresses were wasted within the Class 4 system. Loopback addresses, so anything in the 127 network range is known as a loopback address. So 127, 111, 001, any of those combinations within 127 will test your local network card to make sure connectivity, basically the network card is working if you've got connectivity issues. We will also have a link local address, which is 169.254. Now, these, if you ever booted up a host machine and it couldn't get to a DHCP server, you would get assigned one of these addresses automatically within Windows. Now, testnet address is a special address in the 192 range, just reserved specifically for testnet, teaching and learning. Now, everybody just uses 192.168 really. We don't use the 2 network. We just use a private address. It's much easier. Classful addressing, as I said, was the first set of addresses that we learnt. So they were basically divided up based on the first set 3 bits. So if it was a 10, it's a class, sorry, 0. So if the first bit was a 0, it was between 0 and 127. Class B, the first bit had to be a 1, which made it 128 to 191. And then Class C was 11. And what's next? So 128 and 64. So 192 through to 223. And then if you carried that on, we used to have Class D, which is our multicast. Yeah. And then if you look back in the history, we had that range which was used for testing and research. So that's where D and E networks were. All my lovely Microsoft notifications. You don't need that. So little pie chart sort of shows you how the classes were split up. Now you go, well, that's not too bad. So over 2 million addresses were consumed in Class A. Remember that the entire IPv4 address range only made up about 4 billion addresses. So Class A consumed 2 billion addresses just by itself. The numbers there is the total number of individual networks that could have been created from the Class A, 128 networks. So you do the numbers, you'll come up with those. The original system, you had to register and get issued numbers out of one of these agencies, and they represent the controlling organization for the issuing of IP addresses to everyone. Now, the way they do it is they issue blocks of addresses to the ISPs, and then the ISPs issue them down to the individual users within the ISP network. IPv6, basically the same, but instead of using 32 bits of addresses, we now use 128 bits for the address, which is going to be rather interesting when we go to do binary manipulation. We use hexadecimal notation in IPv6. Came about because of the increase in uptake of technology. We ran out of IPv4. We introduced CIDR notation and network address translation to increase the lifespan of v4. So with v6, we don't need network address translation anymore, and it supports Internet of Things. So we're going to have lots and lots of individual little devices connecting to the network under the Internet of Things as more and more automation comes into play. Now, transition from IPv4 to IPv6 is still happening, and we can run dual stack, which basically runs both v4 and v6 on every device in the network. We can do tunneling, where we tunnel v6 networks through v4 networks, and there's a temporary translation service which translates IPv6 addresses into IPv4. It's not the recommended solution, but it's there. IPv6, as we said earlier, is 128 bits. Now, we use a hexadecimal digit to represent 4 binary digits, just like the worksheets and what I went on through on the whiteboard earlier. And if we look at just the 4 binary on themselves, quick reminder, those are 8, 4, 2, and 1. So we have the range of 0 to 15, and that's our 16-bit value for every hexadecimal. So we have 0 to 9, A to F. Okay, just as a reminder, I know we went through all this last term. So basically, the preferred method of addressing is to write all the lovely grouping together of hexadecimal digits in groups of 4, separated by a colon. Now, having to write this out all the time is going to be problematic for us humans. So we've created some rules that, because we know the number of hextets is going to be consistent. A hextet is made up of 4 hexadecimal digits. Any leading 0 can be removed, and we can rebuild the full address from that by simply, well, it's a leading 0, we know that there's a 0 to be added in there. There's 3 zeros missing from there because it must be 4 digits. And by removing it, it doesn't actually change the value. Okay, so that's one way we can do it. The next rule is we can group several of these hextets together that have just been reduced to zeros and represent it as a double colon. So you can only use this rule once, because if you used it more than once, we wouldn't know how many hextets were replaced. Okay, so we can use it either to represent these 2 hextets being replaced with just having the double colon, or we can use it in there. We can't use it twice. So how's that look? Well, with that, we've got FF02 and all zeros going through to 81. It's a lot easier to type an IP address into a device that is FF02::1 than having all of those individual addresses having to be typed. Now, The bottom one's a bit strange, but all zeros can be represented with a 0 in each hextet, or just as a double column. And chances of that ever being used in a live environment are 0, but it's there. Now, we also have 3 types of addresses within the IPv6 one, but we don't have the broadcast. So a unicast still exists, that's our one-to-one. Our multicast is one-to-many. And then a anycast address is a unicast address that is assigned to multiple devices. So it's a cross between a broadcast and a multicast address. So an anycast address is assigned to multiple devices and they all see it, whereas multicast is all devices are subscribed to a certain address and listen for that address, just like in IPv4. So to start with, it is very simple for addressing. Our network portion is always going to be 64 bits to start with. That's universal across IPv6. And we can still borrow from the host portion to increase the prefix, but one of the nice little things we can do within the IPv6 range is we can just automatically assign host addresses based on MAC addresses. But MAC address is only 64. It's not 64 bits, it's only 48 bits. Yeah, we'll come to that in a minute. Excuse me. So global unicast is where we're just sending directly to our one-on-one. Now, each device on a network will get a link local automatically generated. These are unique to the individual network and they will not be used outside of that network. So that they're just on that link. Then you've got the loopback check address, and then you have your unique local address, which is the FC to FDFF addresses. Again, will be generated, and embedded IPv4 addresses is where we basically convert to make things a little easier for us. Link local basically allows IPv6 to talk to each other just on the local segment only, and they will always start with the destination FE80. So the structure is basically global unicast routing will always be defined. So 2001, 4 hextets, that first one will define where it belongs within the global unicast set of addresses. And they will use typically the first 48 bits, and then you'll get subnet and interface IDs after that. So basically in that 64-bit range, they're saying there is a master set of global routing prefixes, and then there's a set of subnets that are used at the upper tiers for the regional ISPs, and then they'll break them down into smaller portions. So how do you configure IPv6 on a device? Well, basically the same way as you do for IPv4. The only difference is that in this little notation there. So instead of writing IP address, we have to put IPv6 on every command structure that we want to use for IPv6. So there's no difference there as far as that goes. Now, again, we put in the IP address followed by the mask in v4. So we use the dotted decimal in v4. In v6, we use the SIDO notation. So after the IP address is put in, we just put the SIDO notation in for v6. So you don't have to write all those lovely 255s and that within v6. You just say how many bits are being used in the network portion. Again, hosts can be configured with this as well. And another one is the stateless address auto configuration stack, which is a new term we'll look at, which basically is the assignment of the host portion in. So it attains the prefix length from the gateway address, and using Slack, it basically says, okay, I've got the prefix length and default gateway, and using Slack and DHCP, I can generate my own address out of that. And it keeps telling everybody which addresses are used in the network by using those advertisements. So every 200 seconds, these route advertisement messages are sent on that network portion. So Slack is option 1. Slack and stateless DHCP is option 2. And a stateful DHCP v6 is option 3. So you can set up your router to work with one of these 3 options. Or you can work with this lovely UE64 process, which is basically what Slack does. So rather than assigning everything, alright, so remember Slack, you're only getting the prefix length, and alright, so how does it know what its host address is? Well, it uses its MAC address. So the 48 bits of the MAC address is added to, and so in the center where we would split it, because this is a natural boundary between the vendor and the individual network card address, we have an ability to quickly insert another 16 bits into there to take it up to 64 bits. And because every network card is unique on the local segment of network, we generate a 64-bit interface address that is unique to that device. And it's done automatically. Alright, so basically this is your prefix length, and then you get a randomly generated number there, or using the UE process, that address space will be front and rear of that will be made up of your MAC address. Your local link address, your local link is used to determine your gateway. So here, if you see the middle of the address FFFE, you know it's using the UE64 automatic generation for the interface. And you can actually configure manually the local link address on your individual devices if you wish, by putting the option keyword local link at the end of it. So the show command works exactly the same under IPv4 and v6. As I said earlier, we just have to add the v6 to the command structure so it knows we want information about IPv6 routing and address spaces. And we have some packet traces activities to do. Now, I would strongly recommend everybody do both the IPv4 and v6 address space labs, because you might need them both for that skills exam that is at the end of the course. Alright, multicast addresses are working the same as IPv4. So they have the FF02 address space for the multicast, and we have all nodes .1 and all routers .2. Okay, so all routers by default will join this one to listen to routing updates from other routers just straight away. And the .1 is similar to the broadcast address. So we can still send messages to every device using a multicast address. Okay, so that one's. So we're getting the verification. So this is our ping commands and our traceroute commands. So used to confirm the host is reachable, and the way it does this is basically sends out a echo with an echo request on it. So basically it will send out the request and the destination target will send a reply, and it measures the time and routes taken within that. So is there an IPv6 version of it? Yes, there is. Just to make life interesting. Okay. Again, we have to check which protocol we're using. So in the local host, we can confirm addresses for v4 and v6. And remember, if we ping the loopback address, we check the local network card is functioning correctly. So again, ping sends an echo request and waits to hear back for an echo reply. Normally it will send a ping request 5 times, and my writing is terrible this morning. So in a reply, you would get hopefully 5 little exclamation points saying that it's communicated back. You might get a U, which means it was unreachable, and you'll get some statistics on the round trip timer and how many packets were dropped. So if you didn't get the 5 back, say you've got a couple of U's, it might get 3 out of 5 message, something like that. So it works. We've talked about how it works, so I won't continue on along that. Traceroute is useful in that we can determine where potentially to start troubleshooting from using this command. So if we can't get from our source to our destination with the ping, we should start looking at where we can get to as far as the pathing is concerned. Now, if we ping and can get to our gateway and the other side of the gateway address, we might know. So we could ping those. But we don't know what's going on with all these intermediate devices. So by using Traceroute, with what it does is it basically sends a message to here with a lifetime thing. So it'll come to here, run out of time, and get a reply back saying you came here. Then I'll send the next one with the timer incremented by 1, trying to get to here. Gets a reply back. Rinse and repeat for all the devices, and what it builds up is a little table saying you got to router 1, got to router 2, got to router 3, and then got to host 2. And here's our little activities for you to do. So this is where we start really getting into a lot of the hands-on elements of the course. And this is what they call a skills integration challenge. In other words, it's not going to give you a step-by-step function of a lab. It says build this. So this is where it's testing to make sure you've understood the processes that lead up to this point, combines them all together. So you need to do those to reassure yourself that you can pull all that learning together. So within this, we looked at IPv4 and v6 addressing, the dotted decimal notation, the hexadecimal notation, and the rules about shortening IPv6 using removing the leading zeros, and where we have many consecutive zeros, we can remove them with a double colon. And then we had a very quick look at ping and trace routes. Now, you will need to know the difference between trace RT and trace route. Just to give you a heads up, they're used on different devices. So that basically covers chapter 7. Now, most of this chapter you've already done, in that the bulk of it was learning to do those binary to decimal conversions and hexadecimal conversions. So you now can apply that to the IP addressing, because there is going to be questions within the chapter exam on this. And from this point forward, especially with the extra labs and that I'll start to hand out from this point forward, you will be required to create addressing space. So you will need to do those address calculations, work out how to do that. So the next chapter is about creating those address spaces. Okay, so today was the how addresses work. Next week we will go through how to create multiple address spaces from us breaking up a network into smaller address spaces that you can use on your own segments. And from that point onwards, we will be making our own networks and configuring them. So I will be starting to post up little customized labs in preparation for the skills exam at the end. Okay. Any questions on any of that? No? Okay. So your task for today is, for this week, is complete chapter 7. I will enable all the chapter tests again after we finish this session. I will restart this session again at 12 for anybody that's got any questions regarding the chapter. Please work your way through all of those packet tracer activities, and I will check back in 12 if you've got any questions. Again, hit me up via Edmodo, email, or message through My Learning. Any of those sources, I'll be available during the day for a private conversation or answering questions. And this session ID will be used again at midday as our catch up for any questions. All right. There's no questions. I'll let you go and start reading chapter 7.